Imagine discovering that something incredibly simple, something that costs almost nothing, has the ability to cool down an entire building without electricity, machines, or complicated technology. For centuries, people living in some of the hottest places on Earth relied on a basic material that quietly solved a problem modern society spends billions trying to fix. Long before air conditioners, compressors, and refrigerants became part of everyday life, ancient civilizations already understood how to protect their homes from extreme heat. They used a pale mineral coating that could reflect sunlight so effectively that buildings remained noticeably cooler, even under intense summer skies. Today, scientists confirm that this humble substance reflects nearly all incoming sunlight, preventing heat from being absorbed by walls and roofs. In other words, instead of trapping warmth like darker materials do, it sends most of that energy right back into the atmosphere. The principle behind this technique is surprisingly straightforward. When sunlight hits a surface, part of the energy is absorbed and turned into heat, while the rest is reflected away. Dark colors tend to absorb much more energy, which is why asphalt roads, black rooftops, and dark metal structures can become scorching hot during the day. Light-colored surfaces behave very differently. When coated with a highly reflective white mineral layer, walls bounce back the majority of the sun's radiation. This means the structure underneath absorbs far less heat, keeping the interior naturally cooler. In fact, modern laboratory measurements show that some white mineral coatings can reflect up to 98% of sunlight. That level of reflection dramatically reduces how much heat enters a building, often lowering indoor temperatures by several degrees even without any mechanical cooling system. What's fascinating is that this isn't a modern discovery. Thousands of years ago, civilizations around the Mediterranean already understood the power of reflective coatings. The ancient Greeks frequently covered the exterior of homes with a bright white finish that helped them cope with relentless summer heat. Roman builders later incorporated similar materials into their plaster mixtures, using them to protect stone structures from absorbing excessive warmth. Even today, if you look at the famous white villages scattered across islands in the Mediterranean Sea, you'll notice that nearly every building shares the same brilliant pale appearance. Those communities are not simply following an aesthetic tradition. They are continuing a survival strategy that has worked for generations. The coating itself is created from a naturally occurring mineral that has been used by humans for thousands of years. When processed and mixed with water, it forms a smooth liquid that can be brushed onto walls or roofs. Once it dries, it becomes a durable white layer capable of reflecting large amounts of solar radiation. Historically, this mixture was applied to homes not only for cooling but also for sanitation. The material has mild antibacterial properties and was often used to help keep living spaces cleaner in crowded towns where hygiene could be difficult to maintain. So, in many ways, people were solving multiple problems with a single inexpensive solution. In modern times, scientists have begun studying these ancient building techniques with renewed interest. As energy consumption rises and global temperatures continue to climb, researchers are searching for ways to reduce reliance on electricity-hungry cooling systems. Air conditioners are incredibly effective, but they also consume enormous amounts of power and release heat back into the environment. This creates a feedback loop where cities become hotter, which then increases demand for even more cooling. Reflective building materials offer a different approach. Instead of fighting heat after it enters a structure, they prevent most of that heat from entering in the first place. Recent experiments conducted by university research teams have demonstrated how powerful this effect can be. When roofs or walls are coated with highly reflective white materials, the surface temperature under direct sunlight can drop dramatically compared to untreated surfaces. In some cases, these coatings can even create a cooling effect that slightly lowers temperatures below the surrounding air, something scientists call radiative cooling. It's an extraordinary example of how a simple material, something known for millennia, can outperform many modern solutions when used correctly. This rediscovery is forcing architects and engineers to rethink the way buildings interact with sunlight. What earlier societies developed through experience and observation is now being validated by modern physics and climate research. Sometimes, the most effective technologies are not the newest inventions, but the oldest ideas that humanity nearly forgot. While the reflective power of this white mineral coating may sound almost too simple to matter in the modern world, researchers are discovering that its potential impact is far greater than many people realize. In fact, the science behind reflective surfaces has become one of the most promising strategies for reducing heat buildup in cities. Urban areas are particularly vulnerable to what scientists call the urban heat island effect. This phenomenon occurs when buildings, roads, and other infrastructure absorb massive amounts of solar energy during the day and slowly release that heat back into the environment at night. As a result, cities often remain several degrees warmer than surrounding rural areas, especially during the summer months. Dark rooftops, asphalt roads, and dense construction materials trap heat like giant storage batteries, making urban living increasingly uncomfortable and energy intensive. This is where reflective coatings come into play. By covering rooftops and exterior walls with highly reflective materials, buildings can dramatically reduce how much sunlight they absorb. When less heat enters the structure, indoor temperatures remain more stable throughout the day. This means air conditioning systems don't have to work as hard, reducing electricity consumption and lowering energy bills. In regions where cooling systems run for most of the year, even a small reduction in indoor temperature can lead to significant savings. Some studies suggest that reflective roofing alone can lower a building's cooling demand by up to 20%, depending on climate conditions and building design. What makes this approach particularly attractive is its accessibility. Unlike complex cooling technologies that require expensive machinery and maintenance, reflective coatings are relatively easy to apply. Many versions can be brushed, sprayed, or rolled directly onto surfaces, allowing older buildings to be upgraded without major renovations. This makes the method useful not only for modern construction, but also for improving energy efficiency in existing homes, schools, and commercial buildings. For communities struggling with rising electricity costs, this simple solution can provide relief without requiring large infrastructure investments. Scientists have also been exploring advanced versions of reflective coatings that push the concept even further. Some newly developed materials are engineered to reflect sunlight while simultaneously emitting infrared radiation back into the sky. This process, known as passive radiative cooling, allows surfaces to release heat directly into outer space through wavelengths that pass through the atmosphere. In controlled experiments, these advanced coatings have demonstrated the ability to keep surfaces cooler than the surrounding air even during bright daylight hours. The implications are enormous. If widely adopted, these materials could reduce the global demand for mechanical cooling systems, which currently account for a rapidly growing share of worldwide energy consumption. The environmental benefits extend beyond energy savings. Air conditioners and refrigeration systems often rely on chemicals known as refrigerants, many of which can contribute to climate change if released into the atmosphere. By reducing the need for these systems, reflective building technologies indirectly help lower greenhouse gas emissions. Additionally, cooler urban environments can improve public health. During heat waves, excessive temperatures can become dangerous, especially for elderly residents and those without reliable access to air conditioning. Reflective surfaces help moderate these extreme conditions by preventing buildings and streets from turning into heat traps. Another fascinating aspect of this rediscovered technology is how it bridges ancient wisdom with modern innovation. The same principle that helped ancient Mediterranean communities survive intense sunlight is now being refined using cutting-edge material science. Engineers are studying the microscopic structure of reflective minerals to develop coatings that perform even better than traditional versions. By manipulating particle sizes and chemical compositions, they can create surfaces that maximize reflection across a wider range of sunlight wavelengths. The goal is to design materials that maintain their cooling ability for decades, while resisting weather damage, pollution, and discoloration. Despite these advances, the core idea remains surprisingly unchanged. Preventing heat from entering a building is far easier than trying to remove it later. In many ways, reflective coatings represent a shift in how society approaches climate adaptation. Instead of relying solely on energy-intensive machines to fight rising temperatures, we can redesign our built environments to work with natural physics. Sometimes, the most powerful solutions come from understanding how sunlight interacts with the materials around us and using that knowledge to our advantage. As global temperatures continue to rise, the rediscovery of reflective building materials is becoming more than just an interesting architectural trick. It is gradually turning into a serious strategy for dealing with the future of climate and energy. Around the world, governments, researchers, and city planners are beginning to look at reflective surfaces as part of a broader solution to overheating cities. The idea is simple but powerful. If enough rooftops, pavements, and walls reflect sunlight instead of absorbing it, entire neighborhoods could become noticeably cooler. This concept is sometimes referred to as the cool roof or cool city approach, and its potential impact is attracting increasing attention from scientists and urban designers alike. Large metropolitan areas are particularly interested in these strategies because of how dramatically heat accumulates in dense environments. In a typical city, dark rooftops and roads soak up sunlight throughout the day and store that heat in concrete, metal, and asphalt. When the sun sets, those surfaces slowly release the stored warmth, keeping nighttime temperatures higher than they would naturally be. This is why summer nights in cities often feel far hotter than in nearby countryside areas. By replacing dark surfaces with reflective ones, cities can interrupt this cycle. Instead of storing solar energy, buildings bounce much of it back into the atmosphere before it ever becomes heat. Several real-world experiments have already demonstrated how effective this approach can be. In some cities, local governments have started encouraging or even requiring reflective roofing for new construction projects. When large numbers of buildings adopt reflective surfaces, the combined effect can reduce the overall temperature of the surrounding environment. Some studies estimate that if enough rooftops were converted to reflective materials, average urban temperatures could drop by a noticeable margin during peak summer months. Even a reduction of 1 or 2 degrees can make a significant difference in comfort, electricity demand, and public health during heat waves. Another interesting development is how this technology is being adapted for different climates and building types. In hot, sunny regions, reflective roofs are extremely effective because they prevent sunlight from heating the structure throughout the day. In cooler climates, designers sometimes combine reflective materials with insulation systems that maintain indoor warmth during winter, while still reducing overheating in summer. This flexibility makes the technology useful in a wide variety of environments, from desert cities to coastal communities. What makes reflective materials particularly appealing is that they represent a passive solution. Unlike air conditioning systems that constantly consume electricity, reflective surfaces work silently all day long without requiring energy or maintenance. Once applied, the coating simply interacts with sunlight according to the laws of physics. Every ray of light that bounces away from a building is heat that never had the chance to enter. Over time, this passive cooling effect can lead to substantial reductions in energy use, especially in regions where cooling systems run for many hours each day. In recent years, scientists have taken the concept even further by developing ultra-reflective coatings capable of reflecting almost the entire spectrum of visible sunlight. Some experimental paints are so reflective that they can keep surfaces significantly cooler than traditional white paints. Researchers are also exploring coatings that maintain their brightness even after years of exposure to dust, pollution, and weathering. The goal is to create durable materials that cities can apply on a massive scale without frequent replacement. What is remarkable about this entire field is how it connects modern environmental challenges with knowledge that has existed for thousands of years. Ancient builders did not have access to sophisticated climate models or advanced laboratories, yet through observation and experience, they discovered techniques that allowed them to live comfortably in harsh environments. Today, scientists armed with modern instruments are confirming the effectiveness of those methods and refining them for the future. In a world increasingly defined by rising temperatures and growing energy demands, the solution to cooling our cities may not lie entirely in complicated machines or futuristic technologies. Sometimes, the answer is as straightforward as changing the color and material of the surfaces around us. A simple white mineral coating, something known and used for centuries, might quietly become one of the most important tools in designing cooler, more sustainable cities for generations to come.